To ensure that an op-amp is stable when used in feedback, it needs to be compensated. Now, the feedback for an op-amp could be established with resistors, even though this takes DC current out of the op-amp, or you could also use capacitors like this, which is more popular in integrated circuits, although the bias condition is a little bit more fiddly to set up. In both cases, we have the negative input being equal to a feedback factor, which we call beta, times the output voltage. Here we have beta as being the ratio of C2 divided by the sum of the capacitance for the capacitor feedback, or equal to R1 divided by the sum of the two resistors in case of the resistive feedback. It's important to realize that the feedback factor is always really determined by the ratio of some passive components. Now, if the op-amp has a gain, an open loop gain of AFS, we can now find the loop gain as the feedback factor times -1 times the op-amp open loop gain, like so. Now, if one is designing a general op-amp, then we would assume that the worst case situation for the loop gain is that it is equal to the open loop gain, because the maximum value for beta is going to be 1, since there's no gain in the passive feedback network. Now, if we think about the op-amp as a device that has two poles, which is the simplest model that gives realistic results, we can write the op-amp open loop gain like this, where AV is a DC gain and omega 1 and 2 are the poles. Now, if we are looking at what happens up at the higher frequencies, which is where stability becomes an issue, and we assume the two poles are separated, we can ignore this one here, which means that we can write the op-amp open loop gain like this, where omega TA is the op-amp gained bandwidth product. Thus, inserting the expression for the loop gain, we can find that the loop gain is equal to this expression. So with this expression, we can now find the Bode plots of the loop gain, which looks like this, where we have a second pole sitting at the frequency which is omega 2, and we have ignored the +1 for the S, which means that the first pole has been ignored. But this level up here would be beta times the op-amp open loop DC gain. Now, the phase of the loop gain looks like this. Now, if we ignore the +1 for the first pole, we have a phase shift of 90 degrees here. In reality, it will be 180 degrees if we don't ignore that, but what we're really interested in is what's happening up here, so it doesn't actually matter. We got a phase shift of 90 degrees from the second pole like that. Now, what is really important and what determines stability is what happens with the phase at the frequency where the gain is equal to 1, or the loop gain is equal to 1. So the unity loop gain frequency. Now, at that frequency, what the phase is what determines the stability. So the margin that we have from here down to 0 degrees here is the phase margin. Now, if it was the case where the phase margin was less than 0 here, what it would mean is that we would have 180 degrees phase shift, which means that the loop gain would become positive instead of negative. And if that happens at a frequency where the loop gain is still larger than 1, or larger than 0 dB, we would have oscillations in the system, and that would be bad. Now, in reality, you want to have a phase margin which is larger than at least 45 degrees, which is not very good. Probably larger than, say, 75 degrees is better. Now, it is fairly simple to find out what the phase margin is with the two-pole model here. So if we set S equal to J times the frequency at which the loop gain is 1, and then we find the phase up in this equation here, we can see the phase from this one here is 180. We got the phase from the J omega t here, that is 90. And then, so we subtract 90 from the 180, this is the phase we have here. And then the phase from that is going to be then subtracted from what we have left, so 90. And this is then the phase margin, like this, where the angle of this complex number is easy to find because it sits in the first quadrant. So this is just the inverse tangent to that ratio there. So we have the phase margin equal to this expression here. Now what we can see, of course, is that if omega 2 sits right at the point where the unity loop gain, at the unity loop gain frequency, then tangent to that becomes 1, and then tangent to that is 45 degrees. So the borderline of the second order pole is that it sits right at the unity loop gain frequency, which means that in general this drawing is not so good. It's not a good system because the second pole sits at a frequency which is lower than the unity loop gain frequency, and it should be moved up to a higher frequency to have better phase margin. So the next thing we need to look at is the op-amp model. Now the small signal model for an op-amp, or the two-stage op-amp, is very simple. It normally looks like this, where we have the transconductance for the differential pair, the output resistance of the first stage. We have also included some parasitic capacitance for the first stage. We have the transconductance for the common source amplifier, the output resistance for the second stage, and the output capacitance for the second stage, which includes any load capacitance that there might be on the op-amp. Now, putting in the compensation capacitor is then between the input and output of the second stage. Now, for the moment, we'll just ignore the resistor. Now, the dominant pole is, as said earlier, determined by the Miller capacitance of this. So the Miller capacitance is seen at the output of the first stage is this capacitance times the gain of the second stage. And that capacitance is normally a lot larger than that, which means that we can ignore the parasitic capacitance here. And that means that the dominant pole is going to be the Miller capacitance times the output resistance of the first stage, or 1 divided by that, like so, as we have seen before. Now, when the frequency is fairly high, which means that the impedance of the Miller capacitance is fairly low, the Miller capacitance will essentially short circuit the two stages, and that means that the second pole of the amplifier is going to be determined by the capacitance C1 and C2 and the transconductance for that. Now remember, if we short circuit the two stages here, the control voltage for this voltage control current source is the voltage across itself, which means that this looks like a resistor. And because 1 on GM is much larger than RDS, that is going to be completely dominating the impedance. So we can have a fairly accurate estimate of the second pole, which is then going to be equal to GM7 divided by the sum of the two capacitance for the stages. Now you can see why it's a good idea to use an N-channel transistor for the second stage, because it means that GM7 is higher, which means that omega 2 sits at a higher frequency, which means that we have better stability in the amplifier. Now, a term that's sometimes used also for the Miller effect here in the amplifier is pole splitting, and this refers to the rather wonderful effect that if we do not put in the Miller capacitance, then we get a pole from the first stage, which is ROC1, and a pole from the second stage, which is one on RO2C2. So since the transconductance is 1 divided by that is much smaller than the output resistance, you can see omega 2 would be sitting at a much higher frequency that we have from a single stage. Likewise, omega 1 sits at a much lower frequency. And that means instead of having two poles from the individual stages that sit at similar frequency, we have one that sits much lower and one that sits a much higher frequency. So this makes an overall much faster amplifier, since omega 2 has moved up in frequency. Now, the introduction of the compensation capacitor, on the other hand, is also creating a zero. So if we have the situation where the output voltage is 0 volts, that means that there's no current flowing in either of the two load impedances there, which means that all the current flowing in the compensation capacitor also flows in this controlled current source. So we can set up an equation giving the current in the current source being equal to current in the capacitor. The current in the capacitor, if we have 0 volts at the output, is just the voltage across the capacitor, which would then be V out 1, divided by the capacitor impedance, like this. So solving for S here would give you the, let's do that. So S equals GM7 over CC. So we have a 0 given by GM7 on CC as well. Now you can see that this solution for S here, that sits in the right half plane on the real axis, which means that the 0 here is right half plane. Now a right half plane 0 is not particularly good for stability, because what it does is that it drops the phase down by 90 degrees, even if it straightens up the amplitude characteristic. Now that means that we have actually managed to make the amplifier unstable using Miller compensation. Now this instability can be fixed by putting in resistance in series with the compensation capacitor. And if we do that and repeat the same process, we will find that we have a 0 which is given by this expression here. And we can see that by choosing the value of the resistor large enough, we can even move the 0 into the left half plane, which is not a bad thing. This approach is called lead compensation. Now typically you choose the compensation resistor being equal to 1 divided by GM7, which means that the 0 moves up onto infinite frequencies. And in so doing, it is not in the way any longer. Now, so how should we obtain the values for the compensation capacitor and resistor? Well, first you should do is to, probably using a simulator to help you, but you choose the compensation capacitor such that the second pole in the amplifier, which would normally be determined by parasitic components, is larger than the amplifier gain bandwidth product. And you can choose that just by choosing the size of the compensation capacitor. Now doing so will create a 0, as we know, in the amplifier. So after you've done that, you should then find a compensation resistor such that the 0 that is generated is moved to high frequencies. Now typically, I said, it's a really good idea to use a circuit simulator as a tool to aid you in that, because sometimes the hand calculations can be a bit too complex in order to find the value of the components. And you should of course check that this holds for all process corners. And then you're done.